proving the infinitude of primes. And then it's a good thing. Mainly our purpose is to work on content in the book, proof from the books. That's the name of the book. And chapter 1 is the infinitude of primes. Infinitude of primes. And maybe in later videos, depending on your comments, I might see that we need to prove the fundamental theorem of arithmetic, which I'm very happy to go through. And we start with division algorithm theorem, and we go through everything. So after that, we will make sure that everything makes sense, and we are ready to crack on and ready to go. So here's the statement or theorem. There are infinitely many primes. We start with proof 1. Proof 1 is for all proofs, because we are going to do 6 proofs. Let's do the set of primes. Let's denote set of primes as set of all primes. So yeah, let's see how it goes. Proof 1 is by Ecrude. It's very odd. We assume that P is finite. And then we do consider this number. Consider this number n, which is product of primes, all primes. Yeah, since it's finite, this number is finite. And then we add 1. We cannot notice that n is coprime to every prime. In P. Let's say P bar. P over is a set of primes. So from here, the trick is we use fundamental theorem of arithmetic. By fundamental theorem of arithmetic, which we might prove depending on your comments. The general idea is induction, but it has 2 parts: uniqueness and existence. For arithmetic, n is product of primes. Therefore, there exists Q not in P prime. Hence, Q prime divides n. Hence, P prime is not P. It's not a set of prime. Or here I can say this is a contradiction. And then, yeah. This is the first proof. I will directly run very quickly to proof 2. Proof 2 and proof 2 and 3 will be the same idea. Can prove them at the same time. Here we use Fermat's number. Here we use Mason's number. Fermat's number, Fermat's sequence, and there are numbers of this form: 2 to the n plus 1. Mason number is 2 to the p minus 1. For proof 2, we can see that 2 to the n. Let's do this one. We can factorize. We know how to factorize this. This is one of the basic thing we start with when we are doing factorization in mathematics. And then from here, and we can keep factorizing this one, we notice that f of n plus 1 minus 1, 2 is equal to the product of fi's, where I runs from 1 to, can't say from 0, but from 0, it's yeah, from 0 to n. Yeah, as fi's are odd for all I, and by star combined with star, this relation star, fn and fk are co-prime. This is GCD for k less than or equal to n. And from here we can generalize by induction the pairwise co-prime. But we can make this sequence infinity. This sequence can be infinity, can run from 0 to infinity. And if they are pairwise co-prime, so therefore they are infinity many primes. And the same ideas goes here for Mason prime. We just assume. You can see the main idea is proving the prime numbers, but infinity of prime numbers. We use two ideas: the fundamental theorem of arithmetic, saying that these numbers have prime factorization, and the idea of contradiction, where we are assuming they are finite and find contradiction. The same goes with the third proof. We assume P is finite. Can call it P prime, we don't mind. Then if it's finite, it has largest element, say P is the largest element. And let Q divide MP. Q is a prime. By modular notation, 2 to the P is equivalent to 1 mod P mod Q, sorry. So what does this mean? This, by notation, reminding ourselves the order of 2 mod Q It's P. Can't be 1 as 2 is different to 1, so it's P. Therefore, P divide the size of multiplicative group of like the remainders of invertible group, which are size of Q minus 1. Oh, this is the same as saying remembering the Newton, not Newton, sorry, why? Fermat's little theorem, which says this will always be true. So from here now we know that if P divides this, therefore Q is larger than P, which is a contradiction to the fact that we assumed P was the largest. This is the third proof, second, first, and the main. This is not the. These proofs they are in one book which is called Proof from the Books. It's by Martin, and then his last name I don't know how to say it, but it's Martin Eigner. I don't know if we say like that, and with other guy, we always don't care about the second guy, but you know they are the ones who contributed more, no? That's what I think. I remember in high school we used to call books by their authors. Yeah. So from here, okay, let's go to the proof form. Proof is analysis. Those people studying analysis, now they are having fun, where we use a graph to prove the infinity of primes. And to prove the infinity many primes, imagine just start with this graph. Oh, this is bad drawing, but who cares? This is graph y equal to 1 over x, and you can tell. Yeah, now I will be proud of this graph, this sketch. This is not accurate. I mean, they're not scared. Yeah. Used to do this in geography every time, or some random things, but now in mathematics this is not about, it's not about graphs or anything, it's about proving the infinity many primes. But from here you can see that the area under the curve from 1, this was 1, supposed to be 1 to t, or to x, let's say, dt to t is less than the area of them rectangles, which has the area of 1. Here will be 1 over 2, 1 over 3, plus, let's say 1 over n, where we have this. And we can start from left hand side. This is log x. Log x is less than 1 plus 1 over 2, 1 over 3, up to 1 over n. And by fundamental theorem of arithmetic, but here I will always, just to avoid some mistakes, some random cases, at the beginning we don't know if x is 1, no, we don't stress ourselves, no, not x equal to 1, but yeah, just for safety, let's put to that less than or equal. And from we are not going to use fundamental theorem of arithmetic. I don't know if anyone used this abbreviation, but we'll be using them in this video since our name is not anyone. And from here we are going to do directly what these are the product of some some prime and we add them. So like where p is less than or equal to n, or you can say less than or equal to x. Yeah, and I goes to from 0 to something like we don't know, but something like such that we have pi, and I know we are wasting time here, which is, let's say pk. Yeah, up to k, but all it matters, doesn't matter where we reach. But what I'm saying is that this is less than 2, this when added up to infinity, which is p over p minus 1. That we just use for the formula for like this. No, this will be less than 1. It's like a arithmetic geometric progression. So from here now on we can say we know that prime is a prime I. This is pi. Okay, let's call it prime L. Prime L is less than or equal to L plus 1. I mean for larger primes, PL large. And from here, that's why we can say this is, or even after 2 or 3, I think the third prime will be 5. Yeah. Then from here, you can say this is less than or equal to number of primes. Let's use this notation. Px is the number of primes. The denotes number of primes less than or equal to x. So from here we have this p, you can place p as, you can say I from 1 to px, pi over pi minus 1. This is less than or equal to pi equal to 1 px, and you have px, oh sorry, I plus 1 over I. And then from here, I just use this. And from here, I'm trying to be very quick, guys. I'm trying to be very quick, and unfortunately, I'm not that quick. And we can redo the video. There's always time. So from here, we can just say this is px plus 1. So therefore, we prove that number of primes less than or equal to x is always less than or equal to log of x. But we know from our graphing knowledge or from any particular knowledge that log x goes to infinity as x goes to infinity. Therefore, pi of x is not bounded. There are infinitely many primes, in other words. That was proof 4. And then yeah, look at them, they are very nice. Let's quickly go to proof 5 and then 6. Proof 5 uses topology, but we don't need to know any other stuff about topology, just the definition, which we will skip. Only we are going to motivate them open set and cross set and induced topology. Here we define NA to be set of A plus NB. N is an integer, and then also A and B are integers. let's use a and b to be positive integers, to be natural numbers. And then from here we define our open set. Let's say subset of integer is open set if it's empty or for any a in O there exists B such that NA sits in B, sits in O. It's a subset. So from here we can now tell that we can make a notice that every open set is either empty or infinite, as this set is infinity. Remember, we are waiting for contradiction, and then another notice is that NAB is closed set. What does closed set mean? In topology, it's much easier to define some stuff, and closed set will be a set whose complementary is open. So we can see that integer minus NA, and we are working topology on Z. This will be a union of N A plus I B. These are like finding numbers which is remainder A when divided by B. So these are the other remainders. I goes from 1 to B minus 1. So this is open set, this is open set, and union of open sets, which is also finite. So this is open set. Therefore NAB is closed. Now we know by fundamental theorem of arithmetic again, this from like proof 1 to proof 5, we've always used fundamental theorem of arithmetic. We know that all integers other than 1 and negative 1, they can be written, they are divisible by some prime. So here comes our contradiction. If P is finite, then our right hand side is closed, as it's a union, finite union of closed set. So if it's closed, then we require 1 and negative 1 to be open, which is a contradiction to this fact that every open set is either empty or infinite. So this is how they prove that there are infinitely many primes using topology set point of view. So the last one is also another fabulous proof, which we cannot skip. So we prove this is diverges. And the proof is due to Erdos. It's one of the newest proof. And here's how it goes. So here we assume it converges this so what happened then? If it converges, then we know at some point there exists k such that p I to is equal to k plus 1 over p i's less than 1 over 2, because you know if this doesn't happen, then we won't converge. So this will happen, and we mathematicians like to give name things, but some of mathematicians, no, I don't want to give that joke. Let's keep it aside. Okay. Yeah. From now we can define primes with I greater than k to be big primes, and pi's with I less than or equal to k to be small primes. What's next then? Once we've done that, define NB and NS. I'm trying to almost copy and paste the strategies and the proof in the book I mentioned. So I invite everyone to check it out. And if it goes well, we go through it within less than a year, and it's a bit motivating, and should be accessible to anyone. If you finish the undergraduate in maths, that's I thought before starting university, I thought that's one of the advanced works of math, but it's not even close. So here, this is numbers less than numbers of integers less than or equal to n divisible by at least one big prime. Remember on how it defines big prime, and this is the number of n's only divisible by small primes. So where do we go next from this? Oh, hang on a sec. We know that NB plus NS should be, this should hold. Yeah. Is it? Yeah, it should hold because it's either one of the numbers than n, then it should be in this case or this one. So here's the contradiction. You can tell that n 1 over pi which is less than 1 over 2 once you multiply by n. You can also estimate nv, which is all primes. These are all multiples of pi's. Let's say we are doing I greater than or equal to k. Less than also multiples of pi's, but which are less than n, which is this one, and this is less than this, less than this, which is less than n over 2. So now we know NV is less than n over 2. So our proof succeed if NS is at least n over 2. But is this possible? Let's see. NS, let's go any number which are less than n. Let's write them in this form: an bn squared, where an is square free integer part. Since we have k primes, they are 2 to the k square of 3 integer parts. What's next? Yeah, 2 to the k square of 3 integer parts. And also from here I can tell b to the n squared divided by n, which means they are possible values of bn's are squares of n. Therefore, ns is at most 2 to the k times square root of n. To find our contradiction, what we do, we pick n such that 2 to the k times square root of n is less than n over 2. Can put this down as long as this happened, the first one has happened. We get our contradiction since this is equivalent to saying n is greater than or equal to 2 to the 2k plus 2. That's just multiplication and simplification. So this is possible, no? N was there for any integer. So as long as we pick any integer greater than this, we have n be number and ns less than n. This is contradiction. Look at that. Yeah, that's the end, man. Keep updated, keep doing maths. Do 1 hour at least every day, and if you miss one, do 2 hours the next other day. And then maths is very useful to life. I will tell you, this is true. Thank you. Thanks, guys. Can't stop this, and let's see what you've written. Yeah, a lot of things, man. Yeah, I hope you enjoyed, and if you enjoy, show your comments in the comment section, and we will see if you can keep doing some proofs from the book. Yeah, those are the kinds of names mathematicians come up with